Our next speaker is Louis-Philippe Morency. He's going to talk about multimodal perception for user satisfaction estimation.
Thank you very much. Really nice to be here. Really nice talking. I'm passionate about multimodal, about how to bring all this information, heterogeneous information, together. And I will talk today about one specific project related to VR. But just as a side note, I'm also super interested in how these technologies can relate to healthcare, and specifically mental health, and also how we can build social agents as part of these technologies at a high level. But one of them, it was really exciting. Some collaborators at Meta contacted me about 2 years ago and said, we're really interested in sensing, multimodal sensing, and there's a specific use case we have in mind. And this is that, and that was before LLMs and ChatGPT. They were like agents. As we build agents for AR, VR, we want to be able to also personalize, we want to also be able to personalize those agents to allow the user either directly, actively, or passively to to personalize them. And so now it's even more important. We see all these agents and we want to be able to have them the same way when we meet someone, we adjust our behavior, we learn, and I'm a French Canadian, I have a Canadian background and also an American background, and so all of this, and when you meet someone the first time, you adjust your behaviors. And so here we designed the project in a specific way, saying, okay, we have the agents, and recently Meta released Meta AI agents, and tracking AR or VR glasses. And the idea is, instead of having this typical, more very data-intensive, annotator-intensive of RLHF, like reinforcement learning with human feedback, where people say, oh, this was a bad answer, this was a good answer. Can we do it in an automatic way, where we sense the information from the glasses, and from this information, automatically find out when the user satisfaction is positive or negative, and I'm simplifying it because user satisfaction is a very multifaceted problem, but just for the purpose of this talk, let's just think that it is a positive and negative. And the reality is that from a machine learning perspective, this is a very interesting problem because in reality, most of the time, there are a lot of modalities that are going to be missing, partially observed, and noisy. So from a machine learning, it's really interesting. And the other is that we rarely have those labels because they are live interactions. What we really have is other data sets where we do have some label, but they are not within domain. They are out of domain. They're not exactly the same interaction. So from a machine learning and AI perspective, it's a great opportunity for collaborating between industry where there's a clear goal, there's a clear reason to do that. And from an AI and machine learning and academic perspective, there's a great opportunity for students to build and create new algorithms. So I will talk about some of these findings in this specific case because we also hear a lot online about those large language models, or just in general, those big pre-trained models. And now we went from going to pre-trained models only on language, now only on vision, but now we start seeing like Gato and all of those that are training on everything at the same time, those magic pre-trained models. So what we wanted is to see how can we learn from larger and larger number of modalities, like cell phone, AR glasses, VR glasses have a lot more modalities than what we used to have. How do you train? And most data sets, I don't know many data sets that have 10 or 12 modalities. Most data sets have a small number of modalities. But we want to be able to handle a learning from a large because we want to be able to handle missing modalities. And so the idea here is you have a lot of data sets and all of them have a subset of modalities and you would like to learn and train these models. And the typical way to do it, and this is This is us taking all these data sets and implementing, and you're welcome to look at it. The data set is called Multibench. And Multizoo is our implementation of about 15 to 20 state-of-the-art multimodal fusion algorithm. And we tried every model on every data set. And here we have the graph. The blue dots is us trying every model on every data set. That's what the blue dots. And the red are like the best of each as a compromise between always performance. But in AR, VR, we have to also think about efficiency because of computation. So this is just the starting point. And then the next stage is to go ahead and do these large models. One model that share everything, share maybe the unimodal encoder and the multimodal encoders. And when you do this, you get an improvement. There's a lot of improvement on efficiency because suddenly you're sharing a lot of parameters, but there's a trade-off here on performance. So we ask ourselves, can we do better than those very large models that take everything and share everything? And here's the first step in this, was we ask ourselves, which modality are very different versus which modalities naturally combine with each other, that share a lot of information. And it would make sense that instead of trying to merge everything, you start kind of hierarchically with the modalities that are a little bit closer to each other, and then you build from that. Say also is that it's not just which modalities, and that's really what I like about this, is how bimodal interaction are happening, how pairs of modalities interact, because some modalities have a lot of great interaction. Language and visions are the one we know for the most, but what are the other modalities that have this interaction, this synergy that's beyond the... And so what we did is a nice algorithm called HiMMT that studies these two things. First, which modalities have the similar information, and for that we use domain transfer. We train a model on one modality and then see how well it can transfer to the other modalities. And we do that over many data sets to be sure that it generalizes. What it gives us, it tells us which modality nicely generalize when you share parameters versus which modalities do not generalize well when you share parameters. Similarly, we do the bimodal version of that, the pairwise modalities, to see which modalities have similar synergy, similar interaction. So some modalities, language and vision put together, may nicely generalize to, let's say, language and acoustic, but may not generalize well to language and GPS, maybe. And for that reason, then we'll have different, in this case, a set of parameters. What it allows us is now a new multimodal models, but hierarchical in its nature, and the decision when to share is decided by how closely the transfer was successful or not. And we can do the same in the bimodal case. When you take this model, and I will show it again more graphically here, what's really nice is now we get an improvement. We get an improvement because now you get better performance. You didn't force everybody to share all the time. You only share when modalities are relevant to each other. And the last part was kind of, I was pushing my student to like, okay, can we even go to this? And they were like, LP, this is crazy, but let's try it. Can we go to brand new modalities that have low resources? So you train a model from high resource modalities, and now can I transfer it to another modalities that have very little resource for that? It may be because it's a brand new sensor that is about to be released, and so in this case you don't have as much data, but you may have this with some other data, so you may be able, in fact, to bridge the information very nicely. And what was nice is that transfer showed us that using other modalities beyond this new modality. So we have this new modality, but as you add the other modalities that have more data, you get an improvement, and we've seen it on 2 different tasks that are relevant to user satisfaction. So the last part I want to talk about today is that so many people write papers saying, we're doing multimodal fusion. We're doing multimodal fusion. And they say they're doing multimodal fusion because they're learning one big transformer with all the modalities. But then there was this beautiful paper 2 or 3 years ago that said that those big model, nonlinear big transformers may not, in fact, learn those bimodal and trimodal interaction, that they can be approximated by unimodal and late fusion. Unimodal and late fusion, it is an additive model. And it is amazing. So you see those big, large language model, multimodal one, and it can be approximated by the simple or simpler unimodal and just additive at the end. And so that made us think that even though we do all this pre-training, we want to be sure that the model don't learn just what's specific to each modality and at the end do a late addition of it. We want to be sure that it learns the real synergy of interaction of bimodal and trimodal. And here's the solution to learning those unimodal, bimodal, and trimodal. It's so simple. Once you heard it, you're like, that makes sense. Here's a simple solution. We've done that. And the idea is start with simple first. Neural networks are really good at finding shortcuts. They find the easy solution first. If it's multimodal, what do you think is the first solution they will find? It's the unimodal. That's their first thing. They find the unimodal. So what we decided is let's have a model where we factorize the output to be unimodal, bimodal, and trimodal. So the model will output what is unimodal, bimodal, and trimodal. The unimodal is simple to do. You learn 3 models, three separate models, one for each modality, and do late fusion. This is unimodal. Bimodal, you take 2 modalities and train a model, and then do a late fusion as well. But here, as I told you, the neural networks are lazy, and they will find the shortcut. So although I call these bimodal, there are probably a lot of unimodal inside it, just because this is the easy thing to do. I smile, oh, great. I don't need to hear the laughter. I smile, this is happy. That's easy. And the same way the trimodal, although it has 3 modality, it may not have in it, it may include unimodal and bimodal in it. So here's the solution to being sure that the bimodal and trimodal do not learn the unimodal. And the simple solution is to prioritize simple first. What it means is you have a first loss term here for unimodal. That's your loss term. That means do as good as you can with your unimodal. And then you're going to do a residual. Whatever you cannot predict with unimodal, predict it with the bimodal. And whatever you cannot predict with bimodal, predict with trimodal. Very simple, but that ends up learning very good interaction and synergy there. So this is just a first step, an example of a great collaboration between industry and academia. There was a real-world example and use case, but also very interesting AI and machine learning. And that's really a nice step forward for AR and VR. So thank you very much for your attention.